Okay, we'll get started. So thank you all for coming to the seminar. It's on a Friday. Is there a Blue Jays game now or is it later? It's 7. Okay, well I can't say thank you for picking this over the Blue Jays game, but it's good to have you here. It's my distinct pleasure to have Roberto Guardani, who I've known for a number of years. I've had the opportunity to come visit him in São Paulo a few times, and it's great to have you come back and see Toronto for the first time. For the first time, yeah. And São Paulo is a little different than Toronto. We both have highways where people don't move, but that's the only similarity. But air pollution is sort of a shared interest, so I thought it'd be great to get him to come up and give his perspective on some of the work that's going on there. And great to have you here. So I ask you to join me in welcoming Roberto.
Thank you. Thank you very much. Good afternoon, everybody. It's a pleasure for me to be here for the first time. I know Greg since some years, and this opportunity I have to come here. It's a real pleasure to be here among nice people. And okay, the idea of my talk, I have a short introduction to myself, in fact, where we come from, talk a little bit about São Paulo, and a brief description, just an overall description of what we do in São Paulo regarding air pollution quality in my department. This is a topic that is, of course, very broad and it's carried out in different departments in our universities and in other institutions as well. And I'm talking about projects with which I am personally involved. So, I come from South America, Brazil. São Paulo is situated in the southeast of the country, and it's the largest city of the country. And it's a few of them. Here for you to view a forest of buildings, many more than Toronto, of course. And so, the metropolitan area of São Paulo has about 18 million people, and we have now more than 7.5 million cars. So I would say about 8 million cars. And São Paulo is a financial center for the country. It concentrates so 1/4 of the gross domestic product. The main headquarters for a number of companies and banks in the country. We at the University of São Paulo are the largest university in Brazil. This is an aerial photo of the main campus. That's an engineering school where I spend most of my time. And I think the university is different from typical universities, especially in Toronto. It's a very large university. We have 11 major campuses and 4 in the city of São Paulo, like the medical school is in a different campus. And in other cities like São Carlos and so on, a total area of almost 80 square kilometers. So it's a huge land area. We have a total of 36 academic institutes, 6 specialized institutes, and 4 hospitals. So 4 hospitals which belong to the university, education and the community. We have 4 museums. We have a TV channel, radio, or 2 TV channels, radio channels, and so some activities that are not typical for a university, I would say. So it's a really large university. It consumes a little bit more than $1 billion each year, American dollars. And we have a total of almost 50,000 undergraduates in 202 majors, 25,000 graduate students in 230 graduate programs. So the university has about 8,600 places each year, and 150,000 candidates. So people who get into the University of São Paulo are very well selected among students, among candidates in Brazil. So it's a very competitive exam for entrance. We have this entrance exam. I don't know, here in Canada I have similar entrance examinations. Talking about the engineering school, it was founded in 1893 and then it was incorporated by the university by the year of its grounding, its founding in 1934. So the university is a very young university. We have the engineering school has 15 departments, 4.5 undergraduates and 2,000 graduate students. The chemical engineering department, we have 33 faculties, total 60 diplomas per year, and what is special even for Brazil, I think we are the only course in Brazil which has a cooperative structure. For us, this cooperative structure is like that. So the first, it's a 5-year course. The first 2 years is semester-based, so for mathematics, physics, and associated round courses, basic courses. And from the 3rd year on, we start with the courses for the area, for chemical engineering area. And then we have a cooperative structure. That means that there are 4 semester periods between the year and alternating with cooperative work studies in cooperations with companies. So the students spend the whole time during this 4 period cooperative work study in companies. So this is for the students where they can get much more vivid experience with their area, their profession, future profession. So this is the structure of our course. It's the only course in Brazil like that, but I think in Canada you have some universities that have similar structure. The research areas in the department are listed here. That was chemistry, biochemical engineering, food engineering, environmental problems, and process systems engineering. I myself come from the process systems engineering and have migrated somehow to the environmental applications of process engineering, and now recently working in both areas. Main projects we have in our group of process systems engineering, talked about my lab now. So Petrobras, the oil concern in Brazil, is our main partner. We have projects dedicated to control of chemical processes, optimization of processes, and so many things related to process automation. And I listed here 3 of our largest projects. The 3rd one has to do with recovery of metal values from contaminated old mines. It's a big project we have with the Vale company, which is a big mining company in Brazil, and I think they have some facilities here in Canada, so they bought from this company. Like here in your department here, we have some centers, some specific centers, let's say thematic centers. So we have 3. First one is the Petrobras Excellence Center on Process Automation. It's a group built by Petrobras together with USP, based in our lab, and composed with people from both institutions, Petrobras and USP, dedicated to process modeling, control, automation. And second one is Setema. It's located in another city, it's Cubatão. It's a city which is about 60 kilometers far from São Paulo, an industrial site. It's a center dedicated to environmental research. And the third one is a new one. It's a joint project between USP, FAPESP, which is a state foundation to support research, and BG. BG is British Gas. So it's a center dedicated to gas production, gas exploitation, and valorization, let's say, of gas products and natural gas. So it involves transport of gases, involves underwater exploration of gas, natural gas, and valorization of gas, a number of reactions to produce fuels like methanol, like Fischer-Tropsch synthesis. So it involves catalyst development and so on. It's a project of about, the full project is $70 million. It's a largest of our projects now presently in the university, in the engineering school. I myself am involved in, let's say, mainly two topics. First of all, application of remote sensing techniques to the monitoring of atmospheric industrial emissions. It's a project that's being carried out at SEPEMA, which is our Center for Environmental Research, and the development of statistical models for air pollutants prediction. I mentioned another one here, development of optical sensors, which is, in fact, connected to the first one. So I work mostly in the measurement and data treatment dedicated to the remote monitoring of atmospheric emissions and in statistical models for predicting air pollutants in São Paulo and in Bogotá. It's a nice photo of São Paulo in the winter. Our winter is very, I don't know if you can see it. It's not to see, yes. The visibility is very low, but it's taken from a neighbor hill. So it's west part of the city, and winter day, no wind. With the winter day, no wind, and you see a layer of smog resting over the city. I think you can see the blue sky. So this is a typical situation in winter in São Paulo, where you have very dry air, and normally a season where we have high concentration of particles. Our winter, as you may know, is mild, so temperatures rarely go to zero. Normally it's about zero, from 0 to 10 degrees, up to 20 degrees. So then, due to the situation of São Paulo, which is close to the sea and at 700 to 800 meters above sea level, and in a straight line about 30 kilometers from the sea, we have very unstable air conditions, so meteorological conditions. So if you look at plots from, let's say, daily average values of the most important pollutants, you see something like that. There's no periodic move, no characteristic substance tendency. It's always almost like a white noise, chaotic behavior. So it's difficult to predict things for when the pollutants levels behave like that. We have been working in cooperation with SETESP. SETESP is the local state environmental authority in São Paulo to develop models, for instance, for ozone prediction in the São Paulo Metropolitan Area. And what we have been doing is to fit different kinds of multivariate models to historical data on air quality. We have tested neural networks as nonlinear multivariate models, classification techniques like discriminant analysis of different kinds, and decision trees or regression trees too. And in São Paulo, we have, I would say, a very nice network of air monitoring stations, a total of more than 60 stations in the state, and in the city itself, we have more than 30 automatic stations that transmit a number of variables listed, the variables that are present in practically all monitoring stations. And we have, this is automatically transmitted. We store normally hourly averages of these variables. And we have a history of, I think, almost 20 years of data concerning different parts of the city. So it's a huge amount of data. It's a paradise for people wanting to work with data mining techniques. So that's what we do. And some of these projects are being used implemented by the company, by SETESP. So these are some illustrations of things you have. This central of SETESP where they concentrate all data. And for instance, I have made here, just to show you a result, I don't know how used you are to clustering techniques like an art of multivariate analysis, but as you can see in this dendrogram, is that ozone, for instance, which is the main pollutant in São Paulo, present in São Paulo, behaves completely independently from other variables. Like we have measured here visibility at different aims and some other pollutants like SO2 and O. There are variables like the north to south and east to west components of wind direction and particle concentration, and trying to correlate that with ozone. Ozone behaves completely different, completely independently. This is, of course, due to the fact that it's a secondary pollutant, not emitted by anyone, but it's so dependent on other variables that it's very difficult to predict or to correlate it with any other of the normally measured variables. And this is also a result of clustering, which shows the same result, different patterns, specific patterns with high ozone levels. Something came here. Down the orange arrow. Thank you. Okay. Thank you. I don't know why. Okay. Okay. So, just to show you the pattern of behavior of those different variables, when you have high ozone, so it's also a result of cluster analysis. And what we have been doing is to fit neural network-based models, for instance, to data from the network of monitoring stations to predict ozone levels in the city. So we have been working with feed-forward neural networks. Of course, we have been working with different kinds of structures of neural networks, but the ones which have been most successful are feed-forward ones. And okay, a little bit mathematics just to show you that we have each of those neurons in the network. It's a mathematical operator that does basically two things. First is to make a sum, weighted sum of the inputs from in this equation, and then you will apply a response function to this sum, weighted sum. And the response function, of course, you can have different ones. We are mostly using sigmoidal functions, which are this mathematical expression. And the parameters that are adjusted are two: the weight themselves, which are the parameters of all the model, of the parts of the model, and the number of neurons, that means the size of the networks, of the models, complexity of the models we have used. So what we have done is to use as inputs, set of input variables are normally presently used predicted meteorological variables, so predicted by meteorological prediction models provided by institutions that make meteorological predictions. And so we don't use measured values, we use predicted values with different antecedence times and precedence times, and the output is a predicted ozone. For instance, a maximum level during the afternoon, which is when the ozone levels are maximum, and or an average ozone level during a certain period of time. So different configurations. But here's an important aspect, that we use predicted variables, meteorological variables only, no other information, and what we generate is a predicted, for instance, maximum ozone. This is an example of a one-day precedence prediction of maximum ozone in the city of São Paulo, based on a neural network with that structure I just showed. Okay, you get here a correlation coefficient of 95%, so determination coefficient 93, and which is good for a one-day precedence. If you increase the precedence time to 2 days, 3 days, of course, the accuracy goes down, gets worse. But this is the result of two components. First is the unpredictability of the meteorological model itself. And second, of course, the error in the model, in the neural network model. So, but this kind of model has been implemented in the city of São Paulo by SETES, by the environmental agency, and have been used. We have developed this for different parts, different regions of the city. Since the city is so large, I forgot to tell you, but the diameter, if you think average diameter of the city is around 40 kilometers. It's a large region. Another model we have been applying is based on pattern recognition to classify the data in terms of ozone levels. So using, for instance, quadratic discriminant classification. So if you can imagine that you have different groups, I'm just illustrating here 4 different groups of data. If you assume that your data can be classified into 4 different groups, each one with a distribution that can follow a Gaussian function like this one, multivariate Gaussian function, where you have an exponent, in the exponent here, a statistical distance, quadratic statistical distance, sigma here, covariance metrics of the data, and in each group, different groups. The idea is to classify the data based on a discriminant, which is expressed by this equation above, which is the product of the value of the Gaussian distribution in each group times the probability of occurrence of that. That is normally proportional to the number of occurrences of a given group. In the case of ozone levels in São Paulo, we divided the data into, in this case, 4 groups. Yeah? So T1 to T4, and T4 is critical. Concentrations equal or above 200 micrograms per cubic meter, and such techniques has been very successful too. As you can see, if you take that matrix, you see that such model, by using such criteria, data that really belong to this critical group, T4, high ozone concentrations. So about 90% of the data are really allocated by the model to the real group. And so 90% and 1% of the data go to group T3, which is immediately below. And in fact, there is much confusion when you try to classify among group 2 and 3 the data for São Paulo. But at least for the most critical episodes like this, you have a very good success, and high success in the classification. So this is what we have been following lately, and what we have done most recently. I have a student working on using a composition of this and neural networks, and building also trying to organize the data in a random manner and construct different ways, different classification criteria that have been generated randomly. But something, I don't know if you have already heard about a technique called random forests. So a random organization of regression trees. And in fact, instead of regression trees, we're using neural networks as models. So this is, I have a student working on that presently. Okay, second topic I'm involved with is with LIDAR technique, LIDAR. We say LIDAR because it's LIDAR. Light detection and ranging. I don't know how familiar you are with this technique. It's something that has been used since some time, since the 50s, 60s. Even I think one of the first groups that started to use it was here in Toronto, at the University of Toronto. And but this technique has always been used to monitor the atmosphere. So boundary layer, mixing layers, clouds, studying clouds remotely. What we have been trying to do is to monitor the emission, atmospheric emission by industries. And we have been applying that to the Cubatão area, where we have a research center. Cubatão is also close to São Paulo, as I said. an industrial site where we have SEMA, which is our excuse me. Let me see if I don't. Yes. Okay, thank you. And here is where our center, SEMA, is located, indicated in figure. In this area of about 50 square kilometers, we have a part which is residential, 130,000 inhabitants, one large refinery, the third largest refinery in Brazil, one steel plant, one cement plant, and a number of fertilizer and chemical and petrochemical plants. Everybody's emitting to the atmosphere. It's a really nice gas-phase reaction. So when somebody wants to study gas-phase reactions, you have all kinds of acid rain, ammonium sulfate. So, and what we have been done, interesting, and another complicated aspect, the city of Cubatão is at sea level, and as I said, São Paulo is about 800 meters above sea level. And you have a kind of a step here, which is a series of mountains here, around here, and this place is like a shell around Cubatão, 800 meters above sea level. Cubatão is sea level, is above sea level. Here's some water reservoirs, first of all. And what happens is that the dominant wind comes from southeast, makes a kind of eddy here when it encounters the mountains. And so the pollution, which is carried from the industrial area, which is located here, this part, comes to this direction, comes over the city, to the city, and then flows to this water. So it's changing direction, which is very interesting. Yeah. So the city is in a very nice situation. And our center is there purposely. So it's because we have problems of not only air pollution, but water pollution too. And this is the refinery, and what we have been done, and this is the SEPEMA, so in the bottom of the figure. What we have been doing is to point our LiDAR system to a flare, which is located in the indicated place, belongs to a airplane gasoline plant. And so we point our laser from this point to this point, which is situated about 400 meters from SEPEMA. And we have been studying the emission of gases and particles by the flare. And the idea is not to study the flare itself, but to develop a technique for data treatment applied to the flare, which is not a typical application. Nobody uses that pointing to flare, where you have flame, you have hot gases, ionized gases in the flame. So another view. So then the refinery step from mountains. This is Google, of course. And in the same site, we have 5 monitoring stations which measure a number of variables and belong to SETES. And an acoustic radar, so they are in the same site. So we have simultaneously the wind field to 1,000 meters facing this point here. So wind field, velocity and direction of wind. And okay, the LiDAR, I don't know if you are used to this method. It's a post-laser system, works in a similar way as a normal radar, which emits post-electromagnetic waves. In this case, it's optical. So the optical range, we work from the infrared to the ultraviolet over the visible, and it's a post laser, and we measure the back scattered light. So we have from the time difference between emission and reception, you know from which point you are receiving signal. And this brings a very good spatial resolution to the technique. This is the system we have in SEPEMA, in Cubatão. It's a telescope, which is, you can point anywhere, and you can program it to scan or to horizontal and or to be fixed in a point. And we work this system with 3 wavelengths. That's a figure with the system pointing upstairs. You can see the green, which is the visible light here. And this is, at the left, you see the primary measurement you get when you work with such a system. It's the intensity of backscattered light at each wavelength. This is the flash system we have there in Cubatão, and different images of the system operating. And at the right, up right, you can see a bad situation of the flare. So flares are always unstable systems because it's where the refinery is burning everything that cannot be recovered. When they clean a line, for instance, then they send hydrocarbons at high flow rate, and then you generate a lot of soot, like you see in that image. This is a bad situation really. So what we do, this is the top of the flare, and we are pointing our system sequentially in a grid of 12 by 12 locals here, and you get an image from what you have in the flame and above the flame at different planes. So you have, as I said, you have a very good spatial resolution because you can measure it simultaneously. Light coming from different planes, depending on the time difference between emission and reception of the pulse, of each pulse. This is the scheme of the system. And here's what you get as a primary result. You see, this is all in the ultraviolet, so 355 nanometers wavelength, and at different distances, different planes for that grid, 12 by 12. So different planes, different distances from the equipment, from the source. So in this case, each plane is distant 3.75 meters from each other. So you have a very nice spatial resolution that can go to 1 to 2 kilometers far. So you can follow a plume evolving from a stack. That's the idea. So this is the visible, the green, and this is the infrared. And from the ratio of scattering, backscattering, you can get information like here, for instance, you get information on particle concentration, particle number concentration over the grid, and there on the effect, what we call effective diameter. It's a diameter that can be estimated by from the optical model, backscattering model, and at different points from the stack. We are doing now, this is something that we have started to do this year, is to monitor different places in Cubatão. This is an image of the industrial site in Cubatão, full of stacks, and our monitoring system, a van where we can put our LiDAR system inside and go to different places. This is a mobile system we have, and what we have done is to measure, for instance, scanning a region of the atmosphere at different angles and different orientations relative to the north, which is vertical. And what you get is the same as a primary information. Is intensity of backscattered light at each different wavelength, like this, like here in another region. And from this information, you can calculate the rate of emission. This is our objective, but you experiment with this thing, with this kind of information, you can follow the plume based on wind measures simultaneously the wind field, right? So you can follow the plume, and you can, for instance, validate models. Like we have people working on CFD simulation for the same region. So it's a nice way of validating the model because nobody validates models for dispersion. You estimate, and you cannot go there to measure locally. But with LiDAR technique, you can get this information on the concentration, at least comparative rates. And this is what we are doing. So I think this is an idea of what we do there in São Paulo, in my department, projects which I am involved with. want to send a student to work in Cubatão, they're welcome. Thank you. Thank you for your attention.
We do have time for questions.
Yeah, so in the first set of questions about the ozone and so forth, in your extensive database, if I understand correctly, there was no hydrocarbon measurement. Simply the photochemical smog in the
So that's measures hydrocarbons in some specific stations, not in all of them. We have not been used to those data. You're right. Yeah, but they have such measurements in, I think, 10% of their stations. They're measuring hydrocarbons. But we're using data from different stations. And since it's not present in all of them, we are not using it. And the idea is to correlate the scale of prediction models to correlate with meteorological variables only. And this has an assumption, a hidden assumption, that the rate of emission by vehicles doesn't change. And this is, we observe that it's relatively valid during workdays. On weekdays, it changes not in the amount, but in the pattern. So, and what we have been doing lately is to differentiate models for workday models and weekend models, because it emits as much as, but later people start to circulate later, and it's more evenly distributed over the day.
Yeah, you mentioned to me before you started the presentation that a lot of vehicles are ethanol fuel or electric fuel. Do you think that there's a lot of ethanol in terms of evaporative emissions from the cars? Do you think that generates the potential that odor or evaporative emissions from the
Let me ask my wife. My wife is a chemist, and she understands from that. She's not that good in English, but I'm not good either, but she can understand some how the from photochemical precursor, ethanol is better than gas, but they have other problems because they produce all the high. It's a disadvantage.
I'll point out that Luke said that the gas measurements, I was sure the gas measurements are so perfect. But back to the correlation, the neural net model, you were able to predict ozone 1 day ahead.
Yeah, or more.
Or more,
yeah.
With 90% confidence, which is incredibly impressive.
Yes.
But I don't think I can predict the weather an hour from now. So I wonder, did you try taking the actual weather from that 1 day ahead, put it into the model, to see how much the weather is influencing it?
At first, what we did was to use measured variables and to predict. We have made this work until about 3 to 4 years ago, and we published the results. The results were good. With 1 year of precedence, were better than that. But I don't remember the correlation, but it was really good. Yeah, but it doesn't help a lot, because when you need to operate the model, you must rely on predicted variables for the meteorological variables, on predicted values of these variables. And then we gave up using the measured values of the meteorological variables. At first, we wanted only to see if the correlation was clear, and it was really clear. But we worked, in fact, what we do, just go into more detail of that, we work with average values of the predicted variables during the morning and during the afternoon. So, for instance, you have the models generate, for instance, for each hour, the temperature, for instance. So we take the average values of the temperature in the morning, predicted values for the following day in the morning, and the predicted values of the temperature for the afternoon, say from 12 until 5 o'clock. So we use these two variables, the mean values of the temperature, as inputs of predicted temperature. This is the same with humidity, cloud coverage, which is related to radiation, and wind direction and velocity. These are the variables we use, and atmospheric pressure. So mean values of this in each period of the day, 1 day in advance or more days in advance. This is what we're doing now in order to operate the model, because people who want to predict, they use the predicted values. But at first we used measure.
I have a follow-up question. So if the model predicts that there was going to be one of these for over 200 micrograms in 2 days, what sort of interventions? So we predict it to be this high, mostly because of the weather.
Yeah.
We can't control the weather. But there are some things we can do. So what sort of steps are taken in São Paulo in general?
So Paulo, there is a ranking of air quality which is informed. We have in São Paulo, I forgot to bring you, but we have some street clocks. It's not clock, but it informs temperature, weather conditions, the time, and the air quality. So you have a color associated with air quality, which is continuously updated, and you see it in almost every corner in São Paulo. You drive and you see, oh, the air quality is bad. But in fact, you are getting informed about that. There are some recommendations made by the environmental agency in order, so you should not go outside to run at 12 o'clock because you have a high ozone. And these recommendations, they are made. But there is no, for instance, closure of roads or these things, such things that have happened in Paris recently, or no, we don't have that. But in Cubatão, for instance, we have a stoppage of companies of production due to high levels. We have two problems there, SO2 and particles. And you have, when you get to these levels, industries must reduce production. Somehow, I don't know how they do that. How a refinery can reduce production, I don't know.
Which company? The company or the refinery? Who has to stop?
I don't know. Do you know how they control that? Because the test, in this case, they have a special lab or a special office in Cubatão, inside the industrial area, which is responsible for that. So they go to the company, as far as I know, to control it. But I don't know how effective it is. Oh yeah, that's SOCAAR. The prices, there is much movement of trucks in Cubatão. Trucks go to the companies and so big trucks. And this is also done. They walk the street. So walk to reduce standing society. As long as that's the thing that I don't know if they are strong enough to stop that. So try to manage somehow they can reduce it, not all. So let's say a cement company can probably stop or reduce drying step or pre-milling step. But a refinery, okay, a refinery is not emit as much particles, more NOx. But we have a big steel industry there. Yeah, some years ago in São Paulo we had problems with carbon monoxide in the city. And then we had, some years ago, it was in 97, 96, at the end of the 90s. And then what we had was to, there were measures to forbid the circulation of cars. So part of the cars should be based on the number, the registration number. They were obliged to be at home, could not circulate. And this was done in São Paulo in the 90s, century. But then they changed the development of fuels and new cars, so the situation changed a lot. So CO nowadays is far from being a critical problem. So ozone is a critical problem in São Paulo. We have also this circulation forbidden circulation for specific numbers, but this is more due to traffic jam. So 20% of the cars must be home over there, cannot circulate in the city. So one day in the week you must leave your car at home, or you can have two cars. You pay for what you're doing. Yeah. Yeah.
Going back to your model, it seems that your independent predictor variable would have a lot of noise. So how much of your model accuracy is due to the variable itself that you're trying to predict at t+1, the variable at t0? How important is that in relation to comparison to your independent variable, your other independent?
I don't know if I understood your question, but if you, for instance, try to predict x +1, normally in Brazil, since in São Paulo, since you have this chaotic movement, the correlation is really bad.
Okay.
So really bad. So for instance, I learned that I saw in a publication by EPA some years ago that in Los Angeles they used to predict ozone on the following day based on the day before. So the prediction for tomorrow is the same as today because it oscillates so softly. But yeah, so the following day to be 90% of the day of today, and let's say 10% more. So it changes not so abrupt. But in São Paulo, it's impossible to do that. So I don't know if that was your question.
Yeah, no, you answered the question. I was wondering how important the other independent variables were in relationship to the variable itself, the lag variable.
So all the independent variables are changing abruptly too. Yeah. You know, neural networks is always associating scenarios, identifying scenarios. So the pattern of distribution of these variables. And so, in fact, it's too sophisticated model. We have a large number of parameters that you fit. And it's very dangerous to extrapolate, to use such a thing, to use such models to extrapolate, to predict situations that are not within the set of scenarios to which the model was fit. So this is something that you must be very careful because you can associate things that are not associable at all to. So, and the quality of data. Well, I think 90% of the time you lose, or not you lose, but you spend in this work is to clean your data, to avoid outliers and data which are anomalous. Statistical models, they have nothing to do with the phenomenon itself.
Well, if there's no further questions, honestly, thank you very much.
Thank you very much. Thank you for your attention.